Alright, this is the first in, I guess, 3 quick videos that just talk about calculations of bolt forces in particular. The only ways that you can really generate stress in a bolted joint, a typical bolted joint, is either direct shear stress or tension. Tension can be due to the preload on the bolt. It can be due to an external force. It can be due to both. The shear is pretty well always due to some external force. You can certainly get bending into a bolt. It's just not very typical of common joints. If you do have bending in a bolt, you can handle it with typical stress calculations with some sort of MC over I inclusion. But here, the way this is loaded, you're basically twisting this plate about the centroid of the bolt pattern, and as such, there's only torsion applied to these 4 bolts. I'm just going to label them so I know which is which as I start the calculations. Now there's a fairly, right, let's just say a couple of universal assumptions that are made in these sorts of calculations. The first one we're going to say here is that all bolts carry the same load. That's not a good way of putting that. We'll say all bolts. Actually, let's forget about that. Let's say the load is equally distributed to all bolts. Let's just say that the direct shear carried by every bolt is going to be equal. The component of torsional shear carried by every bolt is going to be equal, but when you sum those things up, they're not necessarily going to be equal. The second one is that the plate acts rigidly, and that is that as the load is applied, the load or the plate itself doesn't flex internally. If you took into account plate stiffness, you'd find that different bolts in a pattern would carry different proponents or different proportions of shear, but we're going to say that's just not the case. Now, this assumption primarily works when the bolt pattern is equally spaced. These two things work together and the shear components are the same. If we had a bolt pattern, just for a really quick example, something like that was carrying torsion, the centroid would be out here, and you'd have different radius vectors going out to each bolt. As such, the forces that you calculate there are not going to be the same for every bolt. So what we're dealing with here is sort of specific to the case where the spacing between all the bolts is equal. Now to run this calculation, the approach is similar to what we did with weld calculations, and that is that we first transpose the actual loads to the centroid of the bolt pattern. In welding, we transpose the loads to the centroid of the weld. Here we're doing it relative to the bolts. And this, again, what I'm going to set up here assumes that all of the bolts are the same diameter. If they're not, this process changes a little bit. We'll get to that later. But right now I've got a 1,000-pound load offset by 7 inches. So I know it's going to transfer to the centroid as a force, and then that's also going to create a torque. And here I'm drawing the direct loads exactly as they would look at that centroid. In other words, I'm not drawing reactions. I'm going to put the bolt forces in as reactions. So I'm going to have essentially a direct shear force that's a portion of the 1,000-pound force that acts vertically at all 4. If that splits evenly, that means that every one of those bolts that has to contribute 250 pounds. We'll just say all forces given here are in pounds. And next we've got the contribution of the torque. Now that's going to be, again, I'm going to draw it in the direction that opposes the applied torque. It's always going to be perpendicular to the radius arms as we follow along here. And this one's actually going to be upward, so it's parallel. Bring the labels down, A, B, C, and D. Now just looking at those vectors, I haven't calculated the magnitude of that orange vector yet, but just looking at it, you can see at C, they're in this exact same direction, which means the full magnitude of the orange one adds to the full magnitude of the blue one. That's going to be our worst case value. We can calculate the forces at all 4. Now to get that actual force bolt due to the moment, We have the moment itself is 7,000 pounds. We'll divide that by 1.25 inches. And that gives us the total force carried by all 4 bolts. If we then also divide by 4, that gives us the amount of that force that's carried by the individual bolts. And from that we get 1,400. So again here, the magnitude is the same everywhere of the force due to shear, but when we combine that with the 250 pounds, it's going to vary from bolt to bolt. So we'll summarize all these out here. So FA, they are perpendicular, so we'd have 250 squared plus 1,400 squared, which is 1,422. At FB, we've actually got 250 minus 1,400 if we take just a typical coordinate system. So we'll leave the minus sign on it. At FC, it's actually the same calculation as FA there because they're perpendicular once again. And then at FD, I've swapped some numbers here. That should be FD. This is FC. Same approach. Here we've got 250 plus 1,400, or 1,650. So this one goes sort of up at some angle. This one goes down with a positive magnitude. This one is up at some angle, and this one is all vertical upward. All right, that's where I'm going to stop this one. The stiffness calculation for this we can talk about in class when we meet next. I just want these to focus on the actual force calculations.